All right, so we're going to talk about systems of differential equations. So applications for this are when you have predator-prey relationships, like a two-tank mixing problem. If you have like a spring mass system with two springs, any of these applications will lead to a system of differential equations. So here's just a quick example. Let's say that x is equal to the population of rabbits. And let's say y is equal to the population of foxes. Okay. And so we have dx dt equals 3x minus 1.4 xy. And dy dt is equal to negative y plus 0.8 xy. So what sense can we make of this? Well, I can think about this as that x is the population of rabbits. So I can see that the population of rabbits, if there were no foxes at all, then the population of rabbits would just grow by itself in the absence of foxes, because the rabbits would be able to eat the grass and whatever. But with the amount of foxes that there are, that will decrease if there are more foxes, then the rate of growth rate of the rabbits will go down. And if I look at the foxes here, I can see the foxes are here. I can see that if there were no rabbits at all, I can see the rate of foxes is negative. The dy dt would be negative if there were no rabbits. So the foxes would die out in the absence of rabbits, whereas the rabbits would flourish in the absence of foxes. And so that's one thing that you might notice. And then as there are more rabbits, then that's going to increase the rate of change of the fox population. So you can kind of analyze the way the differential equations look to kind of see like which one's the predator, which one's the prey, and how are the influence of the other population growing, how does that impact that population? So those are some things you can look at. Another thing that you might want to look at is this idea of critical points. That will be when dy dt or dx dt are equal to 0. And so those critical points, those are points when the population is not changing. It's not growing or shrinking. It's just staying constant. And so we want to kind of look at that. So if dx dt were 0, then I would have 0 equals, and I can factor out that x times 3 minus 1.4y. So that happens when x equals 0, or it happens when y is equal to when x equals 0 or when y is equal to, if I do that, it would be 2.14. Okay, and then if I set the other one equal to 0, I would have 0 equals y times negative 1 plus 0.8x. And that happens when y is equal to 0 or when x is equal to 1.25. Okay, and so what you'll find here is that, let's write it this way, y equals 2.14. Okay, so what we'll find here is that if we have the situation where x equals 0, then that would also mean that y was equal to 0. So if x equals 0, y. So our critical points are 0, 0, and 1.25, 2.14. And so if I look at the phase plan for this, so if I look at the phase plane for the system, one second. Okay, so I'm going to, I'm just Googling GeoGebra, system of differential equations in a phase plane. So if you Google that, you should be able to find this like GeoGebra phase plane generator, and you can actually type in the these two equations here, and it will generate the phase plane for you. So if you do that, the phase plane for this particular differential system of differential equations looks like that. It's kind of like has this singularity point here, kind of like concentric circles around that, and then it's doing like this. And so if you drag a point, some point in here, it would look like this, and then kind of go around like that, and it'll have an arrow direction. And then if it's over here somewhere, it'll kind of be doing something kind of like that. So it's saying the population of rabbits and foxes is going to be fluctuating in that way. But when you actually land at the point, which is 1.25, 2.14, the phase plane is just that dot. And then also at 0, 0, there's another critical point. So you can see those two critical points showing up on the actual phase plane. Here's another example. Let's say dx dt equals negative y, and dy dt equals x. Okay, so you can look at the phase plane for this guy and do that again. And so what you'll see is if this is negative y and this one is just x, you see that it just looks like concentric circles if you look at the phase plane. So the phase plane kind of looks like that, and if you had any point out here, you would just have a circle. Sorry, that's supposed to be a perfect circle, but it's not. So yeah, so that's what the phase plane for this guy looks like. And one thing you might notice about this is I can actually compute dy dx by taking dy dt divided by dx dt. And so if I do that, I get x over negative y. This ends up being a separable differential equation. So sometimes these systems of differential equations are such that you can solve them using separable differential equations. So that's kind of a nice thing. So if I separated these, I'd have negative y dy equals x dx, and I integrate both sides, and I get negative 1/2 y squared equals 1/2 x squared plus c. So I get that x squared plus y squared is equal to some constant c. And so that's why we have these concentric circles. So for different values, we'll see different radii of the circle, as we can see here. And then the critical point of this would be here at 0, 0. Because if dx dt equals 0 and dy dt equals 0, that would mean x is 0 and y is 0. So a critical point is when dx dt and dy dt are both 0. And so that is when that's at the point 0, 0. That's your critical point. Okay, so that's one way of solving systems, is you can sometimes use separable differential equations. Okay, another way to solve differential equations let's say we have this system. So we have dx dt equals negative 1/2 x plus y, and dy dt equals negative x minus 1/2 y. So what would be the critical points here? So the critical points would be 0 equals negative 1/2 x plus y, and 0 equals negative x minus 1/2 y. And so, yeah, so I'm going to end up getting, if I eliminate these guys, if I multiply this second one by 2, and add them, I'll get 0 equals negative 2.5x. So I'll get x equals 0, y equals 0 is my critical point of this system of differential equations. Let's take a look at the phase plane and see what they look like. So I have negative 1/2 x plus y for the x prime, and then I have negative x minus 1/2 y for the y. And so if I look at this guy, it actually looks like a spiral. So this is kind of cool. So, so you end up having these kind of like, the phase plane kind of looks like that. And if you click on any point here, it's going to like spiral in to that. So if I think about this in terms of like population dynamics, what's happening is, no matter where you are on the plane, that population is going to spiral in and eventually die out. So both populations will eventually die out is kind of the equilibrium solution there. Okay, so how can we solve this guy? One thing you might notice is it's not separable. So if I did that dy dt over dx dt thing again, it's going to not give me a separable equation. So another thing you can do is you can solve using Laplace transforms. And so if you use Laplace transforms, okay, the Laplace, we need initial values. Okay, so let's say x of 0 equals 1 and y of 0 equals 1. Okay, so now I can take the Laplace transform of both of those differential equations. So I'll get sx minus the initial value, which is 1, equals negative 1/2 x plus y, and then if I take the Laplace of the second equation, I'll get sy minus my initial value of y, which is 1, equals negative x minus 1/2 y. Okay, so I want to solve for x and y, and this will be like, just like we were solving it using algebra or whatever. So I might get on the first one, if I solved that first one for y, so if I solve that first one for y, I'll get y equals sx minus 1 plus 1/2 x. And I can plug in to the second equation. Okay, and then that's going to give me s times sx minus 1 plus 1/2 x minus 1 equals negative x minus 1/2 sx minus 1 plus 1/2 x. Okay, so I plugged that into the second equation. Okay, so I'm going to solve for x now. And so I'm basically going to end up with, I'll do some algebra, and then I'll get s squared minus s plus 5/4 x equals s plus 3/2. And so I can solve that for x. I get x equals, after I do a little bit of finagling here, I'm going to get s plus 3/2 over, if I complete the square, I'll get s plus 1/2 squared plus 1, which I can separate that into s plus 1/2 over s plus 1/2 squared plus 1 plus 1 over s plus a half squared plus 1. Okay, and so if I look at my Laplace transform table, I'll get that x of t equals e to the minus 1/2 t cosine t plus e to the minus 1/2 t sine t. And also plugging all of that back in and solving for y, I'm going to end up getting, I'm just going to put dot, dot, dot. You'll end up getting y of t is equal to e to the minus 1/2 t cosine t minus e to the minus 1/2 t sine t. And so those are your solutions to that system of differential equations. So that's how you would solve that using Laplace transforms. Okay, so let's do one more example. And this is going to be using the method that you see in your textbook, in the Nagel, Saff, and Snyder textbook. And so that is an elimination method. And so if you look back in section 5.2, I think, let me see. Yes. So if you look back in section 5.2 of the Nagel, Saff, and Snyder textbook, it teaches you how to solve systems using the differential operators and the elimination method. Okay, so just real quick, let me talk about a differential operator. If I have some differential equation like y double prime plus y prime minus 6y equals 0, if I had something like that, and I wanted to write this using differential operators, I would write this as, it would be d squared plus d minus 6 operating on y. And so the d is like taking the derivative. So that d squared would mean I'm taking the derivative twice, and then this d would mean I'm taking the derivative once, and then minus 6 times y. So this is the way you would write it in operator notation. And I want you to notice that this is kind of similar to how you would write the characteristic polynomial. You'd have like r squared plus r minus 6 as your characteristic polynomial. And then when you would solve that, you would have r plus 3, r minus 2 equals 0, and your solution would be y equals e to the negative 3, t plus, C1, C2 e to the 2t. So that would be your solution. It's going to be the same solution here. So it's just going to be, once you get to this point and you see that differential operator, you can factor that and you get d plus 3, d minus 2, all operating on y. And so you just are solving that like you would solve any other linear differential equation like this. So you would have y equals e to the minus 3t, C1 plus C2 e to the 2t. So there's your solution. Okay, so now let's do it with a system of differential equations. Okay, so let's say we have this system. Let's say we have x prime plus y prime minus x equal 5, and x prime plus y prime plus y equals 1. Okay, so let's write this in operator notation. So first of all, I'm going to gather all the stuff with x's and gather all the stuff with y's, and I'm going to write that out. So I'll have x prime, so the first one is x prime minus x plus y prime equals 5. And then the second one I'll have x prime plus y prime plus y equals 1. Okay, so now I can write this in operator notation. So I'll have d minus 1 x plus dy equals 5. And then I would have dx plus d plus 1 y equals 1. Okay, and so now I want to eliminate one of my variables, x or y. So if I'm going to do the elimination method, I could multiply this top one. Let's say I want to eliminate y. So I'm going to multiply the top one by d plus 1, and I'll multiply the bottom by negative d. Okay, and so then I'll get d plus 1, d minus 1, x plus d plus 1, d y equals 5 times d plus 1. Or I guess d plus 1 operating on 5. Okay. All right. And then I will have negative d squared x plus, then I'll have d plus 1 times negative d y equals negative d acting on 1, operating on 1. Okay. So, all right. So what do we have here? So if I eliminate these guys, what I'm going to have is the y's are going to be eliminated, and the x's are going to be negative d squared x. Sorry, it's going to be, okay, so it'll be d plus 1, d minus 1, x plus negative d squared x equals d plus 1 operating on 5 plus negative d operating on 1. Okay, so, all right, so let's untangle this right-hand side. So the derivative of 5 is 0. The 1 times 5 is 5. The derivative of 1 is 0. So that's all that side. On this side, I'll have, basically it'll be d squared, so it'll be d squared minus d plus d and then minus 1. So I'll basically, by the time I combine these two, I'll have d squared minus 1 x plus negative d squared x. So I'm going to end up getting just a negative 1 times x. So it'll be negative x equals 5, so x equals negative 5. Okay, and then what about the y? Okay, so now I can plug that back in up here into one of my equations. Okay, so I'm going to substitute that back up into the second one. So I'll get x prime is going to be 0. And so I could sub that in. So I'll get 0 plus y prime plus y equals 1. So I'm subbing it back up into this second equation that I started with. Okay, so it'll be, so I'm going to get d plus 1 y equals 1. And so, so that's going to give me, so that's going to give me a differential equation, which is, linear. Okay, so this is a non-homogeneous differential equation. So you'll have, first of all, you'll have y equals c1 e to the negative t. So that comes from this part, right? Because the characteristic polynomial is, d plus 1. So then that would be this part, and then you could also, to get this non-homogeneous bit, you can add 1 to that. And so that way, when you take the derivative, that 1 will go away, but then so in other words, if I plug this into this differential equation here, I will get y prime is going to be negative c1 e to the minus t, and y will be c1 e to the minus t plus 1. So if I do y prime plus y, I'll get 1. So this is the solution for the y component, and the solution for the x component is x equals negative 5. So I can plug both of those into my original differential equation and see if that works. So my solution were x equal minus 5 and y equals c1 e to the minus t plus 1. Okay, so obviously x prime is just going to be 0, and y prime is going to be negative c1 e to the minus t. And so if I plug all of those into these differential equations, you'll see that it's going to work out. So if I did x prime plus y prime plus y, that's going to give me the 1. If I do x prime plus y prime minus x, that doesn't give me just 5. So I must have messed up something here. Why is that the case? Okay, hang on. Okay, I'm not sure where I went wrong here. But anyway, you kind of get the idea of the method. So the method is you write it using the differential operators, you eliminate one of the variables, and then you try to solve for one of them, plug it back in, solve for the other one. I think the hardest part of this is figuring out how to interpret it back, but usually what you end up with is things that can be solved, using undetermined coefficients or using some of those methods that we had used previously. So I'm going to stop there, and I'll try to fix this later.